Hi. I'm going to present our latest paper called Adaptive Queue Network, On-the-Fly Target Selection for Deep Reinforcement Learning. As you may already know, reinforcement learning can work well. Either it is for solving complex board games, real-world scenarios, or sophisticated environments. However, it is highly sensitive to hyperparameters. This is why researchers have started using automated machine learning for reinforcement learning. The idea is to use an out-of-the-box AutoML strategy to tune the hyperparameters of the RL training, which is composed of a reinforcement learning agent and an environment. However, those methods were not, at the first place, designed for tackling an RL problem. So the RL problem is considered as a black box. And this is, for us, a problem since it ignores RL non-stationarities. In this work, we propose a way to take into account RL non-stationarities. So let's dive in first into queue learning. It takes as input a target network, and then it computes through the optimal Bellman operator the target. And from there, an online network is learned, minimizing this loss, which is taking the online parameters with respect to the target parameters, and minimizes this distance. After a predefined number of gradient steps, the target parameters are updated to the online parameters. And this is where the loss is changing. And this is where the non-stationarity comes. And this is a problem because the loss is non-stationary along the training. And we argue that there's not a single set of hyperparameters that are optimal. And this happens quite a lot because afterwards we continue the training, but with this loss. And then we also update the target parameters after a predefined number of gradient steps. And we do so, we continue the training, and each time we update the target, there's a problem. A naive approach using AutoML for queue learning would result in learning several agents, each with a different set of hyperparameters, doing a grid search, random search, or Bayesian optimization, and looking at the ending performance. This ignores non-stationarities, and it's also requiring more than one training. In this work, we really focus on only training one agent. We start with a target network, and as usual, we apply the optimal Bellman operator. But this time, we will learn in parallel multiple online networks with different hyperparameters. Then we would choose the hyperparameter, or more the online network using a hyperparameter that led to minimizing the TD error. This is our new target update rule. From there, we would see that the non-stationarity is accounted for, and we can start the second iteration with also the different hyperparameters. And then we select using the same rule. And again, the non-stationarity is accounted for. So let's look at the results. First, we tried adaptive soft actor critique on the Mujoko benchmark. We searched over different architectures, learning rates, activation functions, and also optimizers. We can see that the grid search is not performing well when the x-axis is the number of environment steps and the y-axis is the performance. Random search is a lot more sample efficient, but our method is actually even more sample efficient. And it's also more stable across seeds, because when we plot the worst seed across our method, we see that it performs as well as the average performance of random search. When we look at results environment by environment, we see that, so when we look at the individual performances of each hyperparameter that we considered, we see that our algorithm performs similarly to the best single hyperparameters. But which one were chosen during the training? Well, for that, we plot the distribution of the hyperparameters chosen as target across the seeds and along the training. And we see that it has been not the same hyperparameter schedule for each environment, which means that our method builds custom and non-trivial hyperparameter schedules. Thank you for listening.